Alright, we're beginning online class 14, section 7.4 in our book, entitled Estimating Population Mean with Sigma Unknown, November 12, Fall 2012, in Math 125. Alright, I touched on this topic in the face-to-face class. I want to first recall section 7.3. Kind of a salient point here. We were still estimating mu. We were still estimating population means in 7.3, but with the assumption that sigma is known. So this is kind of a big point here. In 7.3, sigma is assumed to be known. Today we're going to be talking about later that what do we do when sigma is unknown? Well, as I said in the face-to-face class, this perhaps is an unrealistic assumption. Perhaps. Recall when you compute a standard deviation. I don't know if you recall the formula from earlier in the semester. You take each value, subtract from it the sample mean, square those differences, add them up, divide by the sample size, take away 1. Well, the idea here is you need the mean to calculate SD. It is required in the formula. Well, recall we are estimating the mean. Well, if we assume sigma to be known in section 7.3. Alright, so if we know the mean, let me rephrase that. If we know the SD, why are we estimating mu? Right? Again, the book gets around this with phrases like, let me write this down, in section 7.3, they kind of get around this this conflict by saying something like a prior study shows your population SD is whatever, or some comment like historically sigma is assumed to be whatever. Alright, well, the bottom line is this. Bottom line, if sigma is known or assumed to be known, we are using a formula based on z-scores. To compute E, our margin of error, and ultimately our confidence interval. And although we've never computed E directly, at least thus far in our course, let me refresh your memory. I've written this down a bunch of times. In this estimating mu scenario, this is our formula for our margin of error. And of course, this formula leads to our confidence interval estimate. Determined by our sample mean minus E and our sample mean plus E. Alright, that's all old stuff. That's all in section 7.3. What I want to do is now talk about, well, what happens when sigma is unknown. In section 7.4, which we'll talk about today, something new today, we're going to be estimating our population mean with sigma unknown. Alright? And the long and short of it is, here, if sigma is unknown, Well, remember, sigma is your population SD. We can substitute our sample SD for sigma in that margin of error formula. So what we're going to do is this. Well, instead of sigma divided by square root of n, we're going to take s divided by the square root of n, and we're going to introduce a new distribution called the t distribution, which we'll talk about in a minute. All right. So the margin of error formula looks largely the same, and again, the calculator computes this value upstream for us. But I do want to talk a little bit about the t distribution before we go out and grind out a couple of examples using essentially a new operator on our stats test submenu. In wide strokes, we'll say this. Approximating sigma with our sample standard deviation. I'll try not to be too formal here. Introduces, we'll call it greater variability. And we'll talk about more about this in our face-to-face class a little bit in more depth. Well, for now, we'll just say using S, substituting S for sigma in this above formula introduces greater variability in our estimates. And what we'll do is use our t distribution to account for this greater variability. Kind of running out of room on the margin here. I hope everybody can see that margin okay. Approximating sigma for S in the margin of error formula introduces greater variability in our confidence interval estimates. Alright. Talk for a minute about what the t distribution is all about. Well, the t distribution looks a lot like the z distribution. In fact, to the naked eye, if you were to graph the t bell-shaped curve over the z bell-shaped curve, you probably won't see much of a difference. It's similar to the z-scores that we're familiar with in previous sections. It's bell-shaped. It has a mean of 0. And most importantly, the t distribution compensates for greater variability or greater spread of scores when using S instead of instead of sigma to calculate E, our margin of error, which is indeed used to construct our confidence interval estimates. Alright, more about this, the mysteries of the t distribution in our face-to-face class. For now, I want to run through some nuts and bolts exercises, introducing a new operator on our calculator list. So I'll ask you to see example 2 on page 358. It's a worked out example in our book, so please pause now and familiarize yourself with this problem. Alright. So the situation here, we're constructing a confidence interval estimate for cholesterol levels. The conjecture is that some sort of garlic treatment may or may not affect the mean level of cholesterol in overall population. Alright, reading through this example, we see we're essentially testing this treatment with a sample of 49. The sample mean, let me read this right out of the book. It says 49 subjects were treated with raw doses of garlic, and their cholesterols were measured before and after the treatment. The changes in their levels of cholesterol have a mean of 0.4. Alright, so the mean change in cholesterol level is 0.4, and a standard deviation of 21. Alright, now note, this standard deviation is not a population standard deviation. It doesn't say that word for word in the problem. It's implied in the context of the problem. And that's going to be part of the game here when you're contrasting 7.3 type problems with 7.4 type problems. This is a sample standard deviation, so we're going to be using the techniques in 7.4 because sigma is unknown. The book doesn't tell you that it's unknown, it just doesn't give it to you, and you have to kind of conjecture that. Okay? Alright, so the sample SD is 21, and the confidence level they want us to use here is 0.95. Kind of a middle of the road. Alright, so to construct this confidence interval with our sample SD given and our population SD unknown, we're going to use the t-interval command. And I think you'll find the mechanics are largely the same as the ones we used in section 7.3. Press your stat button on your calculator, same as before. Select the test sub option and scroll down to reach this t-interval command. Again, we're using t-distribution to estimate the confidence interval when sigma is unknown. Alright, a couple of things have changed from the techniques we used in section 7.3. Well, for the input mode, we are given summary statistics for this sample, so of course we'll use our stats input mode. They asked me for the mean. Well, the sample mean of cholesterol level differences was given as 0.4. Enter that in. Next, the calculator prompts you for CAP-SX. Now remember, in the Texas Instruments language, CAP-SX refers to your sample standard deviation, not population. Alright, the calculator realizes that using this t-interval command implies that your population SD is unknown, so notice they prompt you for a sample SD, not a population SD. Okay? Plug in the sample size is 49, and of course the confidence level is 0.95. Punch this out on your calculator, select, let me write that down. Select calculate, and then hit enter, and the calculator returns this confidence interval. Let me write it down. Alright, so I'll formulate this answer, display this answer like our author likes. I'll say my 95% confidence interval for mu, we're still estimating mu here, will look like this. Minus 5.632 on the low end, positive 6.4319 on the high end, and this is my interval estimate for mu. And again, we can add an interpretive statement. 95% of these similarly constructed interval estimates And remember, we build these based on sample data, so they might change depending on your sample data, will actually contain mu, where mu is the population mean in this problem of cholesterol levels. Alright, so I think you'll agree the structure of the T-interval command is almost identical to the Z-interval command, with the exception that in this line of code they're prompting you for S, not sigma. Okay? Now it's entirely possible to read a problem and use the wrong command to generate the confidence intervals on your calculator, so let me talk about that in a minute. Which to use? The Z-interval command or the T-interval command? And of course you're going to answer me, well, it depends on whether sigma is known or sigma is unknown. Well, as in section 7.3, if sigma is known, we'll use the Z-interval. Actually, there are some other requirements. We'll talk more about this in the face-to-face class. There is a requirement that either the population is known to be normally distributed or your sample size is greater than 30. Don't panic about that right now, but I just want to put it down in writing. And we use the T-interval when sigma is unknown. And again, there's another sub-requirement, we'll call it the population is known to be normal or your sample size is less than 30. Alright, so largely it's the knowledge that you do or do not know sigma which determines if you're going to use the Z-interval command or the T-interval command. Alright, let me grind through another example or two. Let me get a new screen here. Alright, what I want to do is look in the homework list at exercise 18 on page 366. So please turn there now and read through the given information. I'll turn there myself. 66 number 18. Alright, here we're talking about birth weights. A random sample of the birth weights of 186 babies has a mean of 3,103 grams and a standard deviation of 696 grams. Alright, it cites a journal article. These babies were born to mothers who did not use cocaine during their pregnancies. Alright. The first thing I want you to know, well, let's see. Let's write down some of this given information. We are reviewing 186 births in this study. The birth weights have a mean of 3,103 grams. Make sure I write down the numbers right here. And the standard deviation is 696. And I pause for a minute to label this because I want us to realize this standard deviation is from a sample. Remember, the TI language for sample SD is S sub X. Alright. So, and, you know, there's not a neon sign that lights up that says sigma is unknown. That's left for you to dig that out from the context of the problem. Okay? Alright, so we're going to be using the T-interval command as in section 7.4 rather than the Z-interval command as in section 7.3. Okay? That's an important thing to remember and a common mistake that's sometimes made and where students choose the wrong command. Alright, what else are we given here? Well, we're given the confidence level, of course. And it seems most often they're using 0.95, though anything between 0 and 1 is possible. So sigma is unknown. We're going to use the t-interval command. Alright, so again, on your calculator, we'll press the Stat button, select the Test submenu, and then scroll down to reach the t-interval command, and plug in, of course, the following information. Whoops. The input mode, we'll use stats. It is possible to use raw data. Maybe we'll save that for the next face-to-face class on Wednesday. Sample mean, of course, 3103 in grams. Cap SX, sample standard deviation, is 696. Sample size, 186. Confidence level, 0.95. And we punch this out. And of course, we'll select Calculate. Then press Enter. And the calculator returns this confidence interval estimate. Alright, so again, to write this in our author-friendly mode, I'll say 95% confidence interval for mu is, and I think the author would round this off to the nearest gram. Okay, and again, the conjecture is that 95% of the intervals we so construct will actually contain mu, and that sounds reasonable for the birth weight of a baby. Alright. One more example I want to do before we call it a day. Actually, it's two examples built into the same problem. In our text, in exercise 23, on page 367, well, they're talking about two different treatments. So this is a classic application of confidence intervals. Please turn to page 367 and read through exercise 23 and get familiar with that problem statement. And come back when you're ready. Alright. We want to investigate whether magnets are effective for treating back pain. In a study designed to test the effectiveness of magnets for treating back pain, 20 patients were given a treatment with magnets and also a sham treatment without magnets. Well, that's a crude way to say you've got a treatment group and a control group. Pain was measured using a visual analog scale. After giving the magnet treatments, the 20 patients had pain scores with a mean of 5 and an SD of 2.4. Alright, so basically we're going to break this up into two groups, the magnet treatment group and the placebo treatment group. The magnet treatment group, well, this is going to be part A. The question, part A in this section says construct the 95% confidence interval estimate of the mean pain score for patients given the magnet treatment. Alright, so we've got 20 people in this magnet group. The mean pain score, the VAS score, was 5.0. I'll just call it 5. And the standard deviation for this treatment group of the pain score was 2.4. And again, this is a sample SD. Right? Sigma is unknown. And again, it doesn't say it's unknown. You have to kind of realize that from the context of the problem statement. The confidence level here is 0.95. Alright, so I'm going to use the t-interval command to create a confidence interval estimate. And I'll let you punch this out. As in the previous two examples, you hit your Stat button, the Test submenu, scroll down to t-interval, enter the information as given. The 20 sample size, X bar is 5, cap SX is 2.4 as before, and we get a confidence interval estimate in this branch of the problem 3.9, between 3.9 and 6.1. Let me label this. This is my 95% confidence interval for mu. And this was for the people, the group, the sample group treated with magnets. Okay? Alright, as you might expect, they're going to ask us a similar question regarding the placebo group, but of course they've got different information to input in this command. Still with a 20 sample size. If you read through the problem, the mean pain score, the VAS score, was 4.7. Again, the sample SD implied from the context of the problem statement was 2.9. And the confidence level is the same as in part A, 0.95. So again, sigma is unknown, S is given, so we use the T interval command as before. So go ahead and get to that command and plug in the information given above, and we come up with a confidence interval estimate, again rounding off to convenient values. The boundaries are 3.3 and 6.1. And this is my 95% confidence interval for mu based on the sample group using the placebo treatment. Alright, the book asks now a question C. Compare these results in part A and part B. Does the treatment with magnets appear to be effective? Well, here's how our author answers that question. It says the confidence intervals do not differ by very much, so it appears that the magnet treatment and the sham treatment, or placebo treatment, produce similar results. Well, if the results are similar with your treatment group, that implies that perhaps the magnet treatment has little or no effect. All right? So let me summarize that. This is part C. The results suggest, and again that may be a subjective statement, the results suggest that the magnet treatment is ineffective, at least in this experiment. Okay? Alright, so we've done 4 examples with a little background of this T-interval command on our calculator. We're approaching the 29-minute point, so we'll call it a day here. And of course, the folder will be posted for Online Class 14 as usual. So this concludes Online Class 14. Section 7.4, Estimating Population Means with Sigma Unknown. That is all.